Hello, my name is Eero Uustalu, and I'm actually quite a strange person because my official workplace is Tartu University, but I'm living in Tallinn, and I work in Follow Estonia, and I'm teaching some mobile course of physics for the high school students. But that's not the theme today because actually we don't have time for that. I want to tell you something you could do if you have some spectrometer, and especially computerized spectrometer in your school. So I hope you hear me. And first, let's look what are the options for the spectrometers. There are plenty of options. Most are solvable in eBay too, but you should avoid the cheap ones because I have opened the cheap ones, and actually the cheap ones are not very well done very often. So if you open it up, it's terrible. So very often you have some spectrometers bought maybe from Vernier series, or maybe produced by Ocean Optics. Actually, Ocean Optics is one of the best, and Vernier originally ordered their spectrometers from there, but then they started to do order from somewhere else. So actually, those are from somewhere else. So if you have in school something like this, they are a little bit problematic because they are actually intended more for biology. So they have holes for the cuvettes. But you see, if you want to use them just for measuring the intensity, one has to use the optical fiber, and the optical fiber tends to come out. And for that, it's actually not so simple solution. You have to use rubber band and fix it like this, and then it's probably won't come out during the work. But spectral range for those is adequate for most of the experiments we do today. Some are not doable because actually the range for those are something like 350 till 800 nanometers. So if you have something like this, range is a little bigger. Those are a little better instruments already. As you can see here, you can disconnect the cuvette part. Those are made for Ocean Optics, by Ocean Optics for the Vernier. So it's specialized, little bit reduced resolution because it's especially for the educational institutions. Those spectrometers, US per 200, 200 plus, US per 4,000, 2,000, 2,000 plus, 4,000 are rather good, but you never know what you will buy because most of them are made for the special order, so-called original equipment manufacturer order, and they may vary by the resolution and the spectral range. That is 350, 39 till 1020. But you never know what you get because usually sellers, for example, eBay, don't know what they are selling you. They just sell and take the general characteristics from somewhere. So it's a little bit lottery. Why eBay? Because when they are new, they cost a lot, something like thousands. But if you are buying them used, something like this can be bought something like $500–600. Those something like $300, $400 if you're lucky. So it's rather good. Oh, and I have Ocean Optics HAR 2000, and it's higher resolution spectrometer. Therefore, it's much better, and it's very wide range. As you can see, ranges from little lower than 200 nanometers till 1100 nanometers, so very wide range. Usually all the producers have some sort of free software, and this free software is usually adequate for the school. So find the free software for them. Usually they give free software. Originally, Ocean Optic gave the Overture. Now it's called something else. It's something like Ocean View or something like this. You may be a little bit afraid that the software, they inform that software is payable. Yes, it's payable if it's professional version, but usually if you download it, it tells you that after installation that if you are not going to pay, it will be light, and light, it's okay for you. So choose light immediately. Don't choose other. Light is excellent for you. So, and here we are. At the moment we have some peaks, but let's talk what you can do with it. Actually, I have some 9 blocks. I hope I don't forget anything. And first, we have to tell the children what is seeing. So we can see in very low light, we can see black and white, and those cells are sensibility is something like this for those cells. So I like to write immediately on the picture. That's why the picture is a little bit distorted, because otherwise I couldn't project it on the whiteboard. And our color vision comes with conicals which are red sensitive, green sensitive, and blue sensitive. So as you can see, we cannot distinguish actually the spectral lines. All our color vision comes from the different excitation states of those 3 cell types. So we are not spectral sensitives. That's the problem. Let's speak about how we can characterize light at first. So if the surface is white, it means light comes in and reflects. Therefore, most of the light is reflected. If surface is black, light comes in and will be absorbed. If surface is gray, light comes in, it will be partly absorbed, partly reflected. So actually, for other species than we, there are no colors. Actually, at least colors in our meaning, which is different site of excitation of those cells. But actually, there are just, if the surface or object is giving reflection or emitting light on the certain wavelength, and if it's reflecting, then it's white. If partly reflecting, it's gray. If it's absorbing, then it's black. So just explain it to your children. And at first, what is the white light? So what is the white light? What you can show about the white light? So white light source, the main source will be sun. So we'll go here and take the sunlight first. So that's our sunlight. As you can see, it's rather characteristic, and it's mainly, today it's not very bright day, so it's a little bit tilted at the moment to the blue side. Usually the maximum is somewhere here. So sunlight maximum is usually 550 nanometers, and it's the maximum of our sensitivity too, the common sensitivity. So we are rather well adapted species actually for the Earth. So that was the sunlight. Let's make photo of it. So what will be the next possible excitation? Very many times children tell that, okay, it should be the white LED. Let's see what gives white LED. So I put spectrometer here. My light source somewhere. And as you can see, white LED gives completely different picture, but it still excites our sensors. Probably they are a little bit tilted, so I will take this away. So probably they are a little bit like this. So they excite our sensors almost the same like the outside sunlight does. So let's take the picture of that too. So something like this. So what could be the next light source? Let's see. No, that's not a good source. Electric light, the classical electric bulb. Something like this. As you see, it's rather similar to the sunlight. I could adjust the intensity, but actually I don't have time. Sorry. Rather similar to the sunlight, but it's tilted more to the red side. So that's why those sensors are excited more, and they give sensation of yellowish because of that. So let's do the picture of that too. What next? Maybe my mobile, because you see, my mobile screen is actually, it can be white too, like this. Part of it's white. And let's see what's happening here. So what is it? It actually AMOLED. I have to take down the sensitivity, the exposure time at the moment. So, and you can see that we will have 3 peaks. So there are actually 3 LEDs, and there is certain LED to excite certain sensor. Those sensors are 52 actually. Bad picture for me for the first. I was a little bit too hurry at first. So let's do them new. So green is somewhere here, and red is a little bit behind, and blue is here. Okay, and now let's take the last one, which we can offer. So the last one is actually that one here. So I could switch on the lights, they are the same. So it's luminiferous tube, so it's actually like a classical mercury tube with luminiferous substance inside the tube, which transfers the UV light to the white light. So let's see what's happening. As you can see, that white light excites those sensors too. But actually, we can show immediately to our children that it behaves completely different. What will happen? The most problem is that, for example, you go to the shop and want to buy some beige shirt or something else, and there's only that light there. And now what you will have your shirt, which you are going to where? It's nicely reflecting here, for example, like this. It's reflecting nicely here. Not reflecting, maybe like this, but is not reflecting here. And here is reflecting too, and here is reflecting too, for example. And you will choose, it's beige. You go on the street and you will have sunlight. Sunlight excites all those areas too, reflects back, gives some additional blue, and you will have something like lila, some violet thing on you. So that's why you cannot make any color decisions using different light than sunlight. So if you have to make any choosing color decision, then what to choose from them? As we can see, that was the sunlight. And we had electrical light where probably I didn't do the picture for the electrical light, so I will put it back on in a moment. So you see, electrical classical bulb, you can see it's rather similar to the classic sunlight, but little bit yellowish. So best is sunlight. Next option is that, but you will get yellowish. And then maybe white LED. And the next would be, no, not this option, at least. So that was the first section about the white light. Let's do the next ones. So I will clean this up. Put on. Okay, and what we want to discuss now, next thing you can explain to your children is black body radiation laws. So what laws will we have? At first, black body radiation should be shaped, the spectrum should be shaped something like this. So it starts rather sharply and then goes down, but not so fast. So where is energy? Energy is to that direction. So that's energy. To that direction, we have wavelength. Okay. So what's the first law? The intensity will be proportional to the fourth power of the absolute temperature. It means that if we heat it up, it will be higher and tremendously higher. For example, if we compare, for example, sunlight, which is 5,700 kelvins, and our radiation, which is 300 kelvins, the difference is roughly 20 times. So 20 powered to fourth power will mean 160,000 times more intense. So it means where we are. Now we have the shift rule. It means that if that is lambda maximum, then lambda maximum over absolute temperature of the source will be constant. Okay, so what it means? It would mean that if we compare those two sources, here we have maximum around 550 nanometers, And where will be our maximum as source of radiation? It could be then 20 times higher wavelength. So it's somewhere there, and it will be something like 11 micrometers. So rather high. What happens around the 11 micrometers? Let's think. It should be something like this. Here is our maximum. And somewhere high here are those lines, extension of those. So that should be 160 times higher. The scale is 160 times higher. So, but let's show this. For that, I have lamp here. Okay, switch it on. Hopefully it will switch on. Sometimes it, okay, now it's switched on. And let's take some spectrum. Okay. Oh, I took the light off. Like this. So I will clean up the things I wrote here. Okay. At the moment, I will make one picture more because I probably moved the desk. So let's take the first rule, that one. Let's make a little lower voltage now, a little bit lower voltage. And as you can see, it lowers everywhere. Why everywhere? Suppose that in this part here, it goes higher. So how to explain to your children why it's impossible? Second law of thermodynamics. What second law of thermodynamics tells us? It tells that the heat can be self-transferred by himself without additional effort from the body with higher temperature to the body of lower temperature. So that's the direction of heat. To move it backwards, you have to make some effort. So here, if we filter out that part, in here, lower temperature body could transfer heat to the higher temperature body. Therefore, it's impossible. Okay? So let's show the shift. So I will take down the voltage. You'll think that it's nowhere to see, but let's see. I will put on some additional integration time. Let's put something like 1800. Okay. It takes some time usually. Okay, now it's from somewhere else. The source is probably from outside. I will cover it up. Okay, so I can still make it smaller. Is it burning? Not at the moment. It's difficult as I have to use some light for lighting myself. Usually I will put lights down during that, but then you won't see me. So let's take a little bit more down. Okay. And as you can see, we have a shift, very big one, to the infrared side. So children may ask you, why this form here is not like black body radiation should be? Why it has waves on it? So problem is that those spectrometers usually come out calibrated by the wavelengths, but they are not calibrated by the intensity. So for example, if we would have just theoretically some light source which would give something like this for the intensity, then probably the outcome of the spectrometer would be something very different for the intensity. So that may be the problem. So you have to be in condition to explain that to your students. So of course, you can then explain to the children why we are speaking about the black body radiation. Problem was that the first law of radiation tells that the best radiator is the same time the best absorber. But why? You see, if we have having the white surface, then the light comes in and will be reflected. If it's black surface, light comes in and will be absorbed. If light wants to go out, first, white surface, it will be reflected back. If it's black surface, it will be going out immediately. Therefore, the best radiator is black body. And that's why we are telling about the black body radiation. Okay, and now about the black body. So probably any heated surface can emit then the black body radiation. Let's see. So I will take the new picture and now put on a little bit more heat. It's high out at the moment. I have just take it down. Let's put something like 5 here. Okay, it's still high. Okay, and something like this. So that's our light bulb. And let's make a picture of that. Now I will switch it off, as you can see. And I will replace it with a candle. To help with a candle, okay. So that's my candle, but it's moving. But you probably can see that the candle seems to be rather matalan blood. The candles is kind of unstable, so I have to adjust a little bit height. So Now I'm okay. Let's try to make the picture of that. Usually there is no such a moving air around. I don't know how the ventilation here works. Okay, but what we'll have, as you see, the black body radiation from the electrical bulb was here, and that's from the candle. And we see that peak is almost there, and it depends on intensity, but it will repeat himself completely, except those parts here. But I will ask, which are those parts? Let's do a little fast experiment. So I will burn 2 matches, one from one end, another from other end, and wait until they are completely burned. Vaata, kas mul on teatud. Ei ole. Olgu. And let's see. You see, I will put in the match, nothing happens. And now I will put in the match with the head. Let's take the new picture, because the old picture will disturb us a little bit, because there is some photo on. So, and I will a little bit take down the intensity too. And as you can see, I will put in the match with the head. And we'll have very big spectral line there. Now I will remove it, and immediately it will disappear. I will put it in, it will go higher. Now I remove, it will go down. So that's another possibility to create light in spectral lines. So we can excite substances, and they will have electrons. We will be on certain levels. So now we excite them to some level, and when they come back from excited state, they release a photon, and this photon gives one spectral line. So let's see. I will have some substance here, and let's put it in the flame. You can see immediately there appears some yellow spectral line. It's actually sodium. So it's actually ordinary salt I added. And that's how the spectroscopy was created. So we had some black body radiation, which is actually like phone, because it's unanimous. There are no lines in. We heated some substances there, and we got those lines. So there will be always background in classical spectroscopy. So let's see other possible light sources we can see. So what we have more? We have, for example, some diodes. For example, something like this. At the moment, of course, you can see it, probably, because camera can see it a little bit. But myself, I cannot, because it's actually remote. Why camera can see it, I don't have time to explain. It's sorry, but okay. But we can see here that we have nice peak. Oh, I will have to put a little bit more time on something like 30. It's how long the exposure will stay. So let's put some knob which is not operating. It's operating mass volume, but you can see we have some source there. It's here. So the next option, some red diode, like this. Something like this. So children will ask probably, can you show the laser? Of course, we can show the laser. Red laser. You can see that laser is very fine line, not so big. And now let's go lower. What will be lower? You can buy so-called UV lights, UV LEDs, like those. And what they will show up. Something like this. As we can see, we are very, very close to our limit of our resolution because we won't see further here. And why it's violet? When you remember that our cones, the red cone has here some sensitivity, that's why it's violet now. Okay. So let's make a picture of that. So we will have that light, violet. Let's put violet in. And we'll see that it's laser and it's on the same wavelength. So it's something like 405 nanometers. Actually, this red was 655, around 650, 655, 660 nanometers. And green one is around, it's exactly 532, but probably I don't have time to tell you about the green laser for the long, but if we take the spectrum, you can see what? You can see that we have more lines that we are expecting. We can have here line, here, and here. So that's the main source of the laser. That's the secondary light, and that's the doubled one. Okay, I will explain very fast. So what we have, that laser here, it's just infrared laser. After that, there will be a crystal named YAG. And this crystal will emit the 1064 wavelength light. There will be some filter not to let this green light, the original light out, okay? And then there will be non-linear crystal named K, but it was kalium, potassium, KTP. It's sodium, potassium, okay. It's usually used KTP. You can find it easily in the internet exactly why it's named like this. And here the frequency will be doubled and energy will double. So 2 photons will be connected to 1, and we will have on the little bit different direction outgoing light 532 nanometers. So as you can see, there are 3 stages, around 800 nanometers first, then that, and we have evidence here. 3. Okay. And some other source. So we have those lights. And that should be ultraviolet. And it's ultraviolet A. So let's put it on. Ultraviolet A. As you can see, it's rather nice. It's somewhere here. And see those distinctive lines here. They will show actually up that the source is the same tube we had for that light here. You see those. And that's our fluorescent bulb. So fluorescent bulb, the source of fluorescent bulb is mercury vapor, and mercury vapor spectrum is transferred using fluorescence to other wavelengths, and in that lamp case, it will be the UVA. But the original lamp is actually UVC, and it should be seen antibacterial lamps like this. Let's see, can we see? We have all nice lines of mercury spectrum, but not UVC. But why? Because you see the transparent hood, so-called transparent, is not transparent at all in the UV light. So let's remove it. And now we had nice line here. It's 254 UVC. And that kills bacteria, including COVID. So we have some 7 minutes more. Too little, but I try to show how much I can. So we went now to the luminescence part. So I will clean up those sources fast. And our source will be the violet. So I will show the violet. You see, the violet laser. And now I take the money paper, as you can see. And it's white. And white means every light which is on the surface will be reflected back. So it will be not absorb any light. Let's see. That's reflected light. As you can see, only that source is on game. But now I take the white paper and money paper, side by side. You see, money paper, white paper. Big difference. Why is it so? Let's see. I will put something here, and let's make the reflection now. As you can see, we have some additional curve here. Here. And it's explained by luminescence. So we have stages in electrons, energy stages, and usually it goes back and forth if those are not restricted, those transfers. Electron goes back and forth. But sometimes in some substances, we have plenty of stages when the electron goes there by the phonon interactions. It may be stuck here. Why? Because from here down, it's forbidden. And now it's stuck. And as we know, in the world of little particles, we don't have anything forbidden. You just have to wait very long. So they have to wait long here. Therefore, those stages are very long-lived stages. Let's see those long-lived stages. I have here one ball which has a nice luminescence. And I will have here some. And this ball is halved. Now I will excite one of those. And then, as you can see, comparing them, one is luminescenting very, very, very long. So, what are the how you can show the luminescence in your experiments? I have some very nice colored batches here. I just went to the some shop and bought some pieces of fabric. So I will light them with that, and you can see they all luminescence very nicely. So let's take this yellow one first. I will take the spectrum, and you can see nice luminescence. Now I will take the green. We have a few minutes more. I will have the green, and you can see that no luminescence on green. See, no luminescence on green. We have only those green spectrum lines. But why? Because you see, the green, the blue energy was like this, but the green has low energy, and it can be excited from here. But if we would have red fabric, I can show red fabric now. You see? Let's take a picture. Oh, not that. Let's take the picture of red fabric luminescence. Okay. And it's lower. Therefore, where is it? It's here. Those stages. And now I will take the green. And you can see that we are still luminescent nicely. The same luminescence. So now it can be excited.